So number 35a is asking us to find the leading term in the degree of f. So if we write out our function f of x, we get negative 5 times 4x minus 3 to the 5th times 3x plus 1 squared. So when we're looking for the leading term, we're looking for the coefficient and the x associated with the x with the highest power. So we can rewrite this to find the leading term by using just the parts with x in them. That's going to give us the highest power. So if we were to simplify this down, we end up getting negative 46,080 x to the 7th. So this is going to be our leading term, right? And our degree is going to be that power of x. So our degree in this case is 7. Okay, part B is asking about the zeros and their multiplicity. So what we're going to do is we're going to first write out our polynomial again. It's equal to negative 5 times 4x minus 3 to the 5th and times 3x squared. So to find the zeros, we need to take these parts here and set them equal to 0, because that's going to give us a function that equals 0. So if we start with our first one, we have 4x minus 3 equals 0. So then we have 4x equals positive 3, because we add 3 to both sides. And if we divide both sides by 4, we get x is equal to 3 over 4. Great, so that's our first 0. So this is equal to 3 over 4. And the multiplicity of this 0 is going to be 5, and we know that because of this exponent right here. Multiplicity 5. Okay, so for this other one, we're going to have 3x plus 1 is equal to 0. If we subtract 1 from both sides, we get 3x is equal to negative 1. We divide by 3, but x is equal to negative 1/3. So then x is equal to negative 1/3, and the multiplicity for this 0 is going to be 2, and we know that from that exponent right there. So mult 2. Okay, so it's asking us as x approaches negative infinity, f of x approaches what? And as x approaches positive infinity, f of x approaches what? So first we want to kind of sketch out a rough graph of what we know. So we know a couple things. We know our zeros are at negative 3/4 and negative 1/3. And we know because of this negative sign here, right, that this graph is going to start up here. And since the degree is odd, we know that it's going to end down here. So really, that's all we need to know, because we know that as this graph goes negative to negative infinity, as x goes to negative infinity, our graph is spiking going up to infinity, right? And as x approaches positive infinity, as we're going to the right here, right, our graph is going down infinitely. So then our f of x is going to approach negative infinity. Okay, so we are finding a formula for the polynomial with the following characteristics. Write your answer in factored form. Okay, so step 1 is let's draw this. So what we know, we have this graph here. We have a 0 at negative 5. We have a 0 at positive 2, right? And it passes through the point 1, 3. And it says our end behavior is as x approaches negative infinity, f of x approaches infinity. So we're starting up here. And then it says as x approaches infinity, f of x approaches negative infinity. Okay, so we're ending down here. And it has degree 3. So we know one of these zeros is going to bounce. And we know this is going to bounce at negative 5. So our graph is going to look something like this. Right, because it couldn't bounce at 2. Because we have to pass through this point. 1, 3, right? If it bounced at 2, it would look like this. But then it wouldn't pass through our point, and that's just can't happen, right? We need that point. Okay, so now that we kind of have our general formula, or our graph, we need to draw up this formula. So we have some f of x equal to a times x plus 5 and x minus 2. And we know that the plus 5 is going to have a degree of 2. And so now we need to plug in our points and figure out this a value. So if we get 3 to equal f of x, and then we have a, 1 plus 5 squared times 1 minus 2, we end up getting a times 36 times negative 1. So we end up getting a is equal to 3 divided by negative 36. And we can simplify that down to negative 1/12. So that is a. So then we can plug that back into our function, and we can say f of x is equal to negative 1/12 times x plus 5 squared x minus 2. Okay, so it wants us to write a formula for the polynomial shown in the graph. Okay, so we know it passes through these points. It has the zeros negative 4 and 1, and it has to pass through the point negative 3, negative 1.6. Okay, so we know our formula for this is going to be f of x is equal to a times x minus r, x minus s, where r and s are some zeros, but the important thing to note is that these both bounce at negative 4 and negative 1. So these would need to be squared in this specific case, right? So if we plug in our things, we are going to say f of x is equal to a times x plus 4 squared, and then x minus 1 squared. Okay, great. And so we also know that it passes through this specific point, so we're going to use that to find a. And so if we plug in these x and y values in, we get 1.6 equals a times negative 3 plus 4, and then negative 3 minus 1 squared, right? Okay, so we have negative 3 plus 4, that is just going to be 1 squared. So we have 1.6 equals a times 1, and then negative 3 minus 1 is going to be negative 4 squared, is going to give us 16. Okay, and so we get 1 times 16 is just 16. Negative 1.6 equals a times 16. We divide by 16, we end up getting a is equal to negative 0.1. So then our final formula is going to be f of x. We're going to put in that negative 0.1 in for a. We're going to say x plus 4 squared times x minus 1 squared. Okay, so number 38 says, suppose p of x is a polynomial of degree 4 with real coefficients in zeros at negative 5, 0, and 3. Okay, and that passes through the point negative 1a, where a is a positive real number. The long-run behavior of p is, as x approaches negative infinity, p approaches negative infinity, and as x approaches infinity, p approaches negative infinity. Which zeros could have a multiplicity of order 2? Explain. Okay, so let's think about it. So let's draw it. I guess our first step always is to draw. Okay, so we know we have zeros at negative 5, 0, and positive 3. We also know we have some point negative 1, some positive a value. So we know the point can't be down here because that would make the a value negative. So we know the point's going to have to be somewhere up here. Let's just plot it right here for fun. We know that this is negative 1. Okay, so it says our end behavior has both of them being negative infinity. So we know our graph is going to start down and end down. Okay, so now let's think about our polynomial behavior. So we know it has to hit this point. So we know that this graph is going to have to pass through negative 5, and so it can't bounce off negative 5. So as it's passing through negative 5, it hits here, but you can bounce off 1 and then go through 3. Okay, I like that. Okay, let's see if there's another way we can do it. Okay, we know that we have to pass through 5 because we have to hit this point. What if we go through 0, we can bounce off 3 and go down? Yeah, there's no other way that we can do that. Those are only two ways. So either we can bounce off 0 or we can bounce off 3. So our zeros, 0 and 3, can have multiplicity 2. And those are the only ones that can have it. Okay, step 1, let's simplify this equation down just a little bit to help us out. So we have 3 times x plus 8 times x minus 1 over, if we can factor out this, we end up getting x plus 8, x minus 2. So this is going to simplify down to 3 times x minus 1 over x minus 2. To find our intercepts, let's first find our x-intercept. And this happens when our function equals 0, right? And so the only way that can happen is if this top part right here is equal to 0, right? Because we can't divide by a 0, and 3 isn't 0. So it's going to have to be when x minus 1 is equal to 0. So x minus 1 equals 0. That means x is equal to positive 1, and so that's going to be our x-intercept. It's going to be x equals 1. Finding our y-intercept is when x is equal to 0. So if we plug in 0 in for x, so we have g of 0, we get 3 times 0 minus 1 over 0 minus 2. We end up getting negative 3 over negative 2, which ends up being 1.5. So that is our y-intercept, or y is equal to 1.5. Okay, again, for this next part, we are trying to find our horizontal and vertical asymptotes. So we have our simplified function down up here, and our horizontal asymptote is going to be our leading terms right out in front of this fraction. It's going to be both leading terms represented as a fraction. So our leading term for the top part of our fraction is 3, and the leading term for the bottom part of our fraction, even though it's not super obvious, it is just a 1, right? So we're going to have a 1 down there, so this is going to equal 3, which is going to be our horizontal asymptote. So horizontal asymptote equals 3. And we would write that as y equals 3. Now our vertical asymptote is going to happen when we have a discontinuity or an asymptote, right, where x is not defined. And so that's going to happen here when our denominator is equal to 0. So we're going to say x minus 2 equals 0. We add 2 to both sides. We get x is equal to 2. That is where we have our vertical asymptote. Right? And so our VA equals 2. So we'd write that as x is equal to 2.
So now looking at 39C here, determine whether there are any holes in the graph. If so, give the coordinates. Okay, so we factored out our denominator earlier. We said that 3 times x plus 8 times x minus 1 over x plus 8 times x minus 2, right? That's what we had originally, and we canceled these 2 points out. Well, since we did that, it means we have a hole at x is equal to negative 8, because we set that x plus 8 equal to 0. That means we have a hole with this x equals negative 8 value, right? So to find what the coordinate is, we're going to plug negative 8 into this equation of 3 times x minus 1 over x minus 2. So 3 times negative 8 minus 1 over negative 8 minus 2. So we have a y value for our coordinate of 3.5. So now we're looking at 39C or 39D, we want to write our domain. So what we can do is we know that we exist from negative infinity, and what's our first x value we have to stop at? What's going to be our hole at negative 8, and we're not going to include it because it's open there, right? So we can't include it, and we're going to union from, and we're valid from negative 8 to 2. All our points exist between there. We have vertical asymptote at 2, so we can't do anything there. So now we're going to union and pick up from 2 to infinity. Okay, so looking at 40 now, we're going to find an example of a rational function with a vertical asymptote at x equals -5, 0 at x equals 3, a whole at x equals -6, and as x is approaching infinity, we want y to be approaching -2, and as x is approaching -infinity, we want y to be approaching -2 as well. Okay, so we want to start this off. We know that our y function needs to be equal to, we have a 0 at x equals 3, so x minus 3 is going to be one of our parts on top, and our denominator, we're going to have vertical asymptote at x equals -5, so that needs to be on x plus 5 in our denominator. So we have a whole at x equals -6, so for that to be the case, we need to have an x plus 6 in the numerator and the denominator, right? So now all we have to do is plug in a value so that way when we're approaching infinity, y is approaching -2, right? So what we can do is we can just do -2 here, right? So if we are approaching infinity, so if I plugged in a value of approximately so those are going to cancel out, right? If we plugged in a value of 10,000 minus 3 over 10,000 plus 5, right? Those values are going to be so small that they're going to be essentially 1, not going to matter, and we're just going to be getting closer to -2 as we go. The larger and larger we get. Same thing as we're approaching -infinity. Y is equal to -2, -10,000 minus 3 over -10,000 plus 5. Those are essentially just becoming 1, so we're getting closer and closer to -2 that way as well. So that means that our example function is y is equal to -2 times x minus 3 times x plus 6 all over x plus 5 times x plus 6. So looking at 41a, we want to evaluate the limit as x is approaching infinity of 3x squared minus x plus 1 all over 2x squared plus 5. So how I like to think about these is we're going to plug in numbers that are really large for x to see what they get really close to. So start off with the limit as x is approaching infinity. Plug in about 10,000 there. 10,000 squared minus 10,000 plus 1 all over 2 times 10,000 squared plus 5. Watch my calculator real quick. And this gives us a value of 1.4999, right? Then if I plug in the limit as x is approaching infinity, I'm going to plug in 100,000. All over 2 times 100,000 squared plus 5. And this leaves us with 1.499995. So you can see that we're getting very close to 1.5. And the way we can say is that the limit actually is approaching infinity. Our function is approaching 3 over 2. Another way you can see that is that our two powers here, to the power x squared, we can take the ratio of them, of the 3 and the 2, and that's how we get this 3/2 as well. Now we want to look at 41b, right? The limit as x is approaching -infinity of 8x to the -3 plus 5x to the -1 plus 1, right? So for this one, I'm going to write the limit as x is approaching -infinity. I write this as 8 over x cubed plus 5 over x plus 1, right? So if we plug in numbers that are really close to infinity, right? So like 8 over 100,000 cubed plus 5 over 100,000 100,000 plus 1, we can see that these two values here, the 8 over 100 and the 5 over 100,000, those are both getting very, very close to 0, right? So our limit as x is approaching negative infinity of 8x negative 3 plus 5x to the negative 1 plus 1 is going to be equal to 1, because these two values are getting very close to 0, so we're just left with our plus 1. Okay, so for question 42 here, we want to find a possible formula for the rational function g described below. It's going to have two vertical asymptotes. One is at x equals negative 2, one is at x is equal to 3. We're going to have a horizontal asymptote at y is equal to 0. Our g is going to cross the x-axis once at x is equal to 5, so an x-intercept at 5. Pass to the point 4 and then 0.5. Right? So, kind of going to have a g of x. We're going to have a constant term out front that we don't know yet, right? And then we can create the rest of it, right? So, we cross the x-axis once at x is equal to 5. So we need to put an x minus 5 in our numerator. And then we need to create, and we have two vertical asymptotes, so we have to have an x plus 2 and an x is equal, and then an x minus 3 in our denominator, right? All right, and for a graph to have as a horizontal asymptote, our degree of our denominator is going to need to be greater than our degree of our numerator to get it at y is equal to 0, right? So if we factored out our denominator, we're going to have an x squared, and our numerator is going to have an x. So that's what leads us to have our horizontal asymptote at y is equal to 0 here. So now we want to find our a value. So we're going to plug in 0.5 for y, and we're going to plug in 4 for x. 4 plus 2, 4 minus 3. So leaves with 0.5 is equal to a times negative 1 over 6 times 1. So we're going to have 6 times 0, negative 6 times 0.5 is equal to a. So a is equal to negative 3. So our possible formula that describes g is going to be g of x is going to be equal to negative 3 times x minus 5 all over x plus 2 times x minus 3. Okay, we're going to look at our last question, 43 here, for the following function, f of x equal to ax over bx plus c, where a, b, and c are non-zero real numbers. We want to answer the following questions. We want to start with question A. Does f have any horizontal asymptotes? If so, what are they? So, f of x is equal to ax over bx plus c. So we have two x values, right? And they have the same degree of 1. So what we want to do is we just want to take the ratio of their coefficients. So we're going to have a horizontal asymptote at y is equal to a over b. So now we want to look at part b. We want to determine if it has a vertical asymptote. So that happens if our denominator is equal to 0. So we want to set bx plus c equal to 0, and that's, so we're going to subtract c on both sides and left with bx is equal to negative c, and then we're going to divide both sides by b. So we know we have a vertical asymptote at x is equal to negative c over b.